Hello everyone. Welcome. Good to see you all. How many Cognitera points do we have at this point in time? What are we up to? $375 is impressive. Have that many problems been released? If so, I'm really impressed. Some good scores. Anything above 0 is a good start. Good to see. Yeah, I've been happy to see everybody's progress on Cognitera. It's been great to see. And I'll say a little bit more about that here in a second. And it's been honestly great to see, that we've had some fantastic viewership both live and after the fact. Our chat is going to appear now after the fact, so we've changed that setting, which I think is really good. Even my mom has been watching. There's a caveat on that because she'll only watch as long as there's no major conflict with her pottery class. So if she's watching, welcome to her as well. I think we should give her a warm chat welcome too. That would be nice to see. She said, I talked to her today and she said, I see that you're talking to people. Like you'll say, hello, Fred. Hello, Bob. But I'm not entirely sure where that's happening. And I think that's a great example of true maternal love, because I could just be here with no one watching, just live streaming to absolutely no one and having imaginary friends, and she'd still be here. So that's been good to see. So yeah, it's good to see she's getting a warm welcome. Thank you. I appreciate all that. The next question though is, do you think she can find the chat? Can she make her way to the chat? I have every faith in her, but it might take us a little bit of time. All right. So note, to come back to the class, we're going to get started here shortly. And I want to note, we put out some deadlines around the material today. Now this is something people had asked last time that we were on here. There are not deadlines in the classic sense of deadline, so you're not going to get penalized if you don't get your points in before the time that's indicated. But I think they sort of indicate what the expectations are. We've talked about this treadmill of sorts that we want you to stay on. And regardless of what your pacing is, it's good to make sure that you're staying to a certain pace. And so if you're following sort of our first cohort of this Python run of the course, the deadlines will help kind of think of them more as guidelines. So we're calling them soft deadlines. They give you these guidelines as to kind of where your checkpoint should be at that point in time. So if you're ahead of that, great. That's fantastic. But I think it gives us a sense of sort of what you should have done by a certain point in time. If you're not quite there, that's all right too. You can always take the course at your own pace, but if you want to try and make these soft deadlines, we have some resources for you to help. So we launched a Study Buddy channel on our Discord today. Check that out. It's a way for you to, even if you're not in a time zone that's amenable to watching us live here, it's a way of interacting with each other and finding somebody who maybe has sort of a similar background or is at a similar place that you are. And so you're welcome to use our voice channel on Discord too to interact if you'd want to use that to work together. But the Study Buddy channel is really an opportunity there for you to find each other. So please make use of that. And then of course, we always have office hours that we've been running a couple times a week for our subscribers. So please make use of that too. And you can join Philomath to unlock that or just to support us. As always, if you're watching this, thank you for being here. Please make sure to like and subscribe. And just keep watching. That's warms my heart the most to see that we've had quite a few people watch and that so many people are watching our streams for a long period of time and are really engaged. It's awesome to see. And we're actually about to cross a threshold in terms of the channel. So we're going to unlock some new features on Monday, and I'll say more about that on our next stream. So thank you so much. In the meantime, I think we're ready to get started. So let's code. To begin, we're going to work with dictionaries in Python, which other languages might call maps. And so I'm going to have a folder in our source code directory that's called Dictionaries. And inside of that folder, I'll have our standard main.py, or whatever we want to call it, .py file. And we'll just have some starter code here. So it's good practice to say, we're going to have a def main. And I'm going to print something like dictionaries in Python. And then we need to have our special 2 lines to say run the code in this main function. So we say if _name _ is equal to this main string, then I'm going to run the code in main. All right, and that just warms us up. But what we really want to do is build a very specific table. Sort of our goal is to get to the point where I can make, and I've got a figure here. We can make a table like this. And there's a clear biological application for why we would want to make this table. What is this table? Well, this is a table of strings that are substrings of a longer string. And then the values beneath them are the number of times that each of these substrings, in this case having length 3, occurs in the longer string. So CGG occurs once, ACG occurs 3 times, and so forth. TTT occurs 3 times. And there's a natural biological application here. BZ says codon, so if we're thinking of triplets of letters, then yes, we might be indexing, for a given gene, we might be indexing how frequently each triplet of codons or triplet of nucleotides occurs, so that we can think about how often does each triplet occur, which will tell us how often each amino acid in the peptide that this string of DNA encodes occurs. Now, that having been said, that's just a coincidence here for this particular application. I want to think about why we might compile a table like this in a biological application from the perspective of you might have a region of DNA where for example, there's some protein that binds to the DNA in some way. So it comes in, it's able to it has weak affinity for DNA in general, but these proteins that bind to DNA will have a specific sequence or a specific string of nucleotides that the protein is looking to bind to. And there is a natural evolutionary argument, which is that if you have a lot of copies of that thing that it's looking to bind to, you're going to be an organism that has greater fitness. And why? Because mutations happen to our DNA all the time. And so when these mutations happen, you're going to be more fit if you're robust to the mutation. So if you have multiple copies, there's multiple opportunities for the protein to bind, and also a disruption because of the mutation gives us the chance to bind to that location with greater likelihood. And so we're going to see sort of build up to that particular application. But what we need to make is a table like this, where I go through a string and I say, what are the substrings of my string of a certain length? And how many times does each one occur? Because the frequency might indicate to me that there's a signal here. And I'll use a larger value of k in the application that we're going to see later. But for now, this is just our introduction to the topic that I want to give you. The other thing I want to point out is that this looks a lot like an array. In many cases, it's very similar to how we think about a list in Python, or more generally an array, in that you have a bunch of elements and each element is associated with some value. And the only difference here is that, well, instead of this index being 0 and this being 1 and this being 2 and so forth, in other words, thinking about the indices as integers, this is our first element, this is our second element, this is our third element, and so forth. We're thinking of the indices as strings because this is a function of sorts that's mapping, not a function in the literal computer science sense, but we're associating each string that we see with a number, which may represent, in this particular case, it's telling me the frequency that each of these substrings occurs in the longer string. So this is why it's not surprising that we cover this somewhat closely after we've covered lists, because dictionaries are related to lists. I'll say a little bit more about that here in a moment. In the meantime, I would like to show you how to start working with dictionaries, and I'll give you an example of something that's going to be a preview of something that we see soon. And that preview that we see soon is that I'm going to have a dictionary that represents having keys, or these indices are going to be names of states in the United States. And then the values are going to be the percentages that a particular political candidate will be polling at that point in time. And so, for example, a presidential candidate. And there's nothing wrong with the way that I've declared my dictionary. So this is sort of the standard dictionary declaration if your dictionary is empty. But I know exactly what this dictionary is going to contain. This dictionary is going to represent a map, or a dictionary, that takes strings, which are state names, and associates percentages, which are floats, to each state. So in thinking more broadly, Python actually gives us a nice feature which allows us to think about the dictionary that we're working with in a sense that is much more generic and that thinks about things like types. And so if I know that my dictionary is, let's call it polls, if I know that my dictionary polls is going to be a dictionary whose indices, or whose keys, are strings and whose values are floats, then I'm going to just go ahead and declare that. So it's almost like a type hint. I can indicate just to the user or to myself that I understand that these map strings to floats. And then at the end of the day, I'm not going to initialize this with any values. So I'm going to just give it open and closed braces to say, this is an empty dictionary. And I'm going to add some elements. So let's add some elements to our hypothetical polls. And I'm going to say polls of Pennsylvania. Let's start off with Pennsylvania, since that's where I'm coming to you from, is 0.517. So for whatever candidate this is, there's a 51.7% polling percentage for this particular candidate. All right, and I'm adding a few others. So I'm fortunate to live in a swing state, which is good because one of my favorite things in the world is fracking. And it's good that on a national level that becomes very important every 4 years. But let's add a few other states. Ohio next door to us is going to be 0.488. These are just made up values. Texas is going to be 0.378. And Florida can never make up its mind about anything. And so we're going to give it a 0.5 because it's going to be a 50-50. So this is our initial map. It's not mapping strings to integers. It's doing something a little bit different. It's mapping strings, which are just names of the states, to these percentages that presumably are going to fall between 0 and 1. I would hope so. And because it's similar to a list, we can get the number of things in this dictionary by accessing length. So we're still going to have a built-in length operator. And I can say, for example, that the number of states, or the number of elements in my dictionary is, and then just say length of polls. So that goes in and it identifies how many keys I've placed in the dictionary, or key value pairs I have. And I can go ahead and run this. So let's do that. Let's save our code, and then let's bring up a new terminal. And I'm in the Python directory, so I'm going to navigate into src/dictionaries. And I want to run my code by saying Python 3 because I'm on a Mac, or Python if I'm on a Windows machine. And then I want to type out main.py since that's the name of my file. And then I want to hit enter. And when I hit enter, this will say the number of elements in my dictionary is equal to 4. So far, so good. Now, before I continue, just a brief remark. And that is that this looks a lot like lists. And there is I think, a temptation among some programmers who might be working with this stuff for the first time to think, well, I only need one of the two. And isn't a dictionary more general than a list. I mean, I can map anything I like to anything else. And I could say, you know, for example, I could set primes equal to an empty dictionary. I could specify the type here as well. But I'm just, for the sake of argument, going to say, well, I could set my first element of primes equal to 2. And I could set my next element of primes equal to 3. And the next one equal to 5, and etc. And this is really bad. Do not do this, because we want to use lists where they're appropriate. And anytime you have a numbered collection of things, where I know this is the first thing, the second thing, this is the third thing, everything is built in for you with using lists. And dictionaries provide this additional overhead that you're simply not going to need. So dictionaries are this generic form of a list in a certain sense, although there's a lot of technical details behind the scenes. But when we're using a collection of variables, if I know that those have an order, this would be a really bad thing to do. I want to make sure that I always use lists where they're appropriate and use dictionaries where they're appropriate. So the next thing I might do then is to say, what happens if you tried to access something that's not a key? So a key value pair in your dictionary that just isn't there. And for example, what if I tried to print poles of poor little old Vermont? What would happen? And I could save this and hit up and run it again. And I'm going to get what's called a key error. And so the key error here is because it is not the case that Vermont is a key of the dictionary. So the things that are our new indices are called the keys of the dictionary. So here is Pennsylvania, Ohio, Texas, and Florida. Vermont is notably not one of those. So if I tried to access the value associated with it, I'm going to get an error since it doesn't exist, which seems really good. Instead, let's give it a value. So I may as well go ahead and say I can add elements to the map or the dictionary anytime that I like. And I could set poles of Vermont equal to some other percentage value. Okay, let's set it to 0.69. Nice. And save that and run it. And now everything is going to be okay. The other thing is, so we're comfortable with adding an element to a dictionary. What if we want to remove something? So we need to go in the other direction as well. For example, let's do all of us and the entire world a favor, and let's get rid of Florida once and for all. So I can do that with a simple built-in command, which is just calling del, which is short for delete, and then whatever the value that I want to get rid of. So in this case, we're going to say del poles of Florida. To be clear, I am moving to Tampa. I mean, that's a good question. I am moving to Tampa, but this is going to be right before it gets sawn off the rest of the U.S. and just floats out into the Gulf of whatever we call it now. So I still like Tampa. There's not going to be any Tampa hate tolerated. But for now, what I will point out is, we could, for example, print poles, and it'll show us that Florida is gone. We probably should be a little more careful here, because I know for a fact at this point in time that Florida is definitely a key in my dictionary. But if we want to be completely precise, we should specify if it's in the dictionary, we can get rid of it, just so we can say, look, I want to say if it's the case that Florida is in the poles. And this is an opportunity for me to show you this notion of how do you check in the first place if something is a key in the dictionary that you have. So you take your key name, which in this case is the string Florida, and you can just have an if statement that says if this thing is true, this will evaluate to true or false, which is nice. So if it's true, well, then we're going to delete it. If it's false, it's not in the dictionary, and so I don't need to delete it in the first place. So there's like hidden parentheses around this, right? that's evaluating to something like this. So is it the case that Florida in the polls is equal to true? But we've just become comfortable with not needing to write if statements like that at this point in the course, which is good. The next thing I would say is, let's say I wanted to create a small list. We know how to do that, and I'm going to wind up commenting this out, but we can create a small list with a list literal. So for example, before we could create like a list of the primes, which is better than creating this dictionary that we had before. And this list of the primes, I'm just going to put 5 primes in there. 2, 3, 5, 7, 11. All right. And this was a way of saying, I know the 5 elements that at least initially go into my list. That's just a recall. There's a literal for dictionaries as well. And I can do this by saying, let's say for a moment, I want to introduce a separate dictionary. So this dictionary, and this is another dictionary that we will work with soon, is that not only do you need to know what's the polling percentage for a candidate in each state if you're going to make an election projection. The other thing that's important about the US presidential election is each state garners a different collection of total votes that get, so its weighting as part of the voting process is the contribution based somewhat on its population. And so there is or there at least is a correlation there. So this is going to be a dictionary that stores all that information, and I'm going to show it for a few states. So we're going to say, I'm going to have another dictionary that maps strings to integers, and in this particular case, I'll just say, instead of it being empty braces, I'm going to hit equal and then have the braces. And you'll notice that what happened, I'll show it again, is that when I type the braces and then hit enter, it will go ahead and give me an indentation there. That's nice. So here I can go ahead and specify the pairs that I care about. Before I had to say whatever the name of the dictionary was, and then whatever the key value is, and then is equal to the value that's associated with that key. Now I can just give it pairs. So this is very convenient. So, and a lot of languages would have this, but we might say Pennsylvania is going to get 20 electoral college votes. So it has a weighting of 20. Ohio is going to get a weighting of 18. And Texas is going to get a weighting of 38. Right? I don't have Vermont's. It's not many. And these are helpful in this particular case of, well, if I know I just want a very short mapping of a collection of things to the values that are associated with them. And we'll work more with this when it comes time for this application, but it's a perfect preview of it. They're also helpful. I want to take a moment and come back to something that we've done previously, which is that we wrote a function that complemented a DNA string. So in a previous code along, we had a function that took a string that we called DNA, and it returned a string as a result of this process. I'm not going to give the doc string, or I'm not going to do anything with checking the parameters here, but I'm going to remind you of how this function works. It takes the string, and so if it has a string of A's, C's, G's, and T's, it simply produces a new string, and that new string results from taking the base pairs and replacing A with a T, T with an A, G with a C, and C with a G in the new string. And there were a number of ways to write this, but one way would be to say, we could start with an empty string, which I'm going to eventually return. And it's not the most efficient way of doing it, but I think it's going to be the quickest. And before, we had two ways of seeing how to write this function. So I'd say before, we could use if and else if statements, or a match statement. And a match statement is called a switch in other languages. Dictionary literals are super helpful in this particular case because they'll often replace a switch statement or a collection of if and else if statements. So I could set a little dictionary that's going to represent the mapping that I care about. I could say complement dictionary, and I'll say, and I need to know this is a dictionary mapping strings to strings. And now I'm going to say, here is what it is. It will map an A to a T. It will map a T to an A C to a G, and a G to a C. And then what we could do is to say, now range over the string and identify and set the appropriate value of DNA2. Okay. So I can range and say for, and in this particular case, I could say for symbol in DNA. So I don't need to an index I or anything like this. It's just going to be ranging over the elements of the string. So the elements of a string are symbols. So anytime you range over a string in this way, it's nice to just call it symbol. And then you see at every point in time, I have an A, a T, a G, or a C. And I probably should check as well that I am at the same time ensuring that it's an A, a T, a C, or a G, and it's not some other letter. But in the meantime, I'm just going to assume that that's okay to show you that DNA2 is going to have concatenated to it. Well, I'm going to say, what is it, an A, a T, a C, or a G? And in any particular case, the symbol that I care about is the value associated with the key, where the key is the current symbol. So I can just say, I could even be really precise. Actually, I know what the current symbol is, it's symbol. And so I want to go in and access the complement dictionary of symbol. And when I grab that, I will be appending the symbol that I want. So if it's an A, I'm going to go in and I'm going to get a T. If it's a T, I'm going to get an A, and so forth. All right, and that makes things much more straightforward than what we had before and easy to read. We need to handle potential errors and so forth, but I think this is a way that is eminently more readable than using a long if and else if statement or a switch statement even. But to come back to where we were and talking about dictionaries and connect them more to ongoing questions and trying to produce these frequency tables, one thing that we should know is, in order to work with dictionaries, what happens when we pass them into a function? So just like with anything else, a dictionary, like a list or an integer or a string, it can be an input to a function or it could be returned by a function. And so let's imagine then that we want to update some dictionary. And here's a dictionary that we want to update in front of us, which is this electoral votes dictionary. So you may know that these electoral votes update every so often, every 4 years, based off of updated populations, the number of votes associated to each state as part of the presidential election can change. And there's a lot of reasons for this and why they fluctuate over time, but these are actually the numbers from 2020. And between 2020 and 2024, a lot of people fled Rust Belt states like my own of Pennsylvania and like Ohio for places like Texas. And who could blame them? I mean, Texas has warmer weather, it's got lower taxes, it's got plentiful ammunition. But in the meantime, I want to write a function that does this. So we're going to say update votes 2024. And I'm going to have an electoral votes dictionary. So I'm going to call it the same thing. In fact, I can make sure that it's clear that this could take a different dictionary. And I'm going to just call it votes. And I'm going to say it is a string dictionary of strings to integers. So I'm still specifying what the dictionary type is in the type hints, which is convenient. And all I'm going to do is update these votes. So I'm going to say, I was calling it electoral votes. Let's set votes of Pennsylvania equal to 19. And we're going to set votes of Ohio equal to 17. So they each lost a vote, and Texas picked up the two that Pennsylvania and Ohio lost. So votes of Texas is equal to 40. Now, this isn't going to return anything. So two points about that. Number one, if you're not returning anything, there's even a type hint for that, which I like. And that's to say there's a special keyword called none with a capital N that indicates I know that we're not returning anything. So I probably should have a little doc string here. I might not specify the inputs or outputs or anything, but what we should say is updates electoral vote, college votes from 2020 to 2024. And let's be precise. We say parameters. We have votes is a dictionary of strings to integers representing a map of states to votes, and returns, and here's where I'm going to say none. So this updates the dictionary what's called in place, meaning that I'm going to pass this into the function, and then it's going to get updated in the function, and we're not going to return anything. So that's what we do here. Now, here's my opportunity to ask you a question, which is, let's call this function in main. If I go to main, here's the end of main where I declared electoral votes. And what I'm going to do is, let's call update votes 2024 of electoral votes. And at the end of this, I want to say, as of 2024, the number of votes in, and let's say Pennsylvania is, and I'm going to go in and I'm going to access electoral votes of Pennsylvania. And my question for you is, what is going to get printed? It is not a trick question in the sense that there are only really two possibilities, right? The possibility could be that 20 gets printed. After all, I didn't return anything in the function. Or it could be that the update to Pennsylvania happens and we print that the number of electoral votes for Pennsylvania is 19. So there's two parts to the question really. It's, what do you think is going to get printed, 20 or 19? And the second part of the question is, why do you think that is? Can we, in one sentence, explain why it would be the case that it would be either 20 or 19? What's the fancy term? Now, there seems to be general agreement on 19. One person says 20, I like it. I like anyone being a maverick. You'd fit in well in Texas. But there's general agreement that we think it's going to be 19. And the reason why is we think dictionaries are passed by reference. So let's see. Let's save this. And let's run it. Indeed, the answer is 19. Now, again, what we have seen throughout the course is I always use this as an opportunity to say, is this particular variable type that we are working with, is it passed by value or passed by reference? And what we've seen thus far in the course is it depends. Integers, strings, built-in types like that are all passed by value. Tuples are also passed by value, but we have seen that lists are passed by reference. And if a dictionary is kind of, sort of, at least initially, and as it's presented to the user, if it seems like kind of a generic list, then it makes sense that it would be passed by reference. And that is the case. So dictionaries are passed by reference. And the technical answer is that this is still not quite right, and there's one way of thinking about all of this that will make it make sense. But you have to join me for the object-oriented part of the course before we see exactly what is going on, and then the light's going to completely come on. So it's not as if they are like, well, we're arbitrarily picking some of these things to be passed by value and other things to be passed by reference. When we have more of that object-oriented approach, it's going to make more sense. But we're going to hold off for now. For now, we don't have to remember that many things. We just know lists and dictionaries are passed by reference. Everything else we've seen is passed by value, where a copy is created. So we can introduce dictionaries, we can add elements to them, we can take elements out. They can be used as inputs to functions or outputs to functions. The next thing that you're probably curious about is, what's the next thing we did when we worked with lists? We learned how to range over every single item in the list. And so that's what we should do with dictionaries too. So I have my electoral votes dictionary. Let's work with that just for a minute. And so I'll say ranging over dictionaries. The most natural thing to do would be to just say, in the same way that we've seen this in our notation here, like we think about a string as a tuple of symbols. And so when you range over a tuple or a list and you just say for blah in blank, well, what you get is all of the values, all of the elements in that list or tuple. So this gives you the symbols because it's not giving you the indices, it's giving you the values. So then the point is, what happens when I do the same thing for a dictionary? When I do for something in electoral votes, what is it that it gives me? And you could imagine maybe there's a lot of possible answers to this, right? It could give you the keys and the values together. It could give you the values, or it could give you the keys. The answer is that in this way of ranging over a dictionary, you get the key. Okay, so I could call it key. I guess I could call it state or state name or something like that too. Whatever you call it, this is a variable that you have control over, is that in this way of writing the range, you get all of the keys of your map or dictionary. So I could use it in this way and maybe print the number of votes in, and then the key is, and then in this particular case, the electoral votes of key. So the value associated with that is just to access whatever the dictionary name is, and then brackets whatever you called the key. Now, when I run this, what we'll see is all these things got updated. So these are the 2024 updates. Number of votes in Pennsylvania is 19, Ohio 17, Texas is 40. So we get this prettier print by ranging over the keys. You'll notice too, and you might have wondered, I can hide it. The question would be, well, what is the order in which these keys get ranged over? Because in the case of lists, we know what the order should be. It should be 0 up to the length of the list minus 1. And I don't think there was any disagreement or thought otherwise when we were ranging over a list that made the most sense. You wouldn't start with element 17. And so when we work with something like our frequency table, though, looking back at this, there's nothing particularly special about CGG versus TTC or ACG. You've lost any sort of natural ordering. And so you might wonder, well, what's the order that these things are going to come out in? Maybe they come out in some kind of special order of the keys, or maybe they come out in no predictable order. And so this is something that has changed over time in Python. These days, the order of the keys that are going to get accessed is based off of the order that you put them into the dictionary that you're working with. Okay, so even though this is a simple ranging, when we range, the order is based on the order in which elements were added to the dictionary. Even if you update, like if I'd gone in and I'd set these values and then I update one of them, I guess I did update them in the electoral votes function or update votes function, it's not going to change this. Okay, so it's based off of the order in which they were initially placed into the dictionary. So you see that the initial order was Pennsylvania, Ohio, Texas, which is what's preserved here. Of course, you might want a special way, like we've seen a way of ranging over indices and the values in a list. And you might imagine that we would have the same need for the same sort of thing. Like, I don't want to necessarily access electoral votes of key. I would like to say num votes, okay? And that should be the pair that's associated with the key. We think of everything in the dictionary as a pair of keys and values. So if I want to do this in a list, I would say it would just be I, or whatever the integer is, comma, num votes, and then I would have that enumerate of what we work with. And for a list, that was what you had to have to specify that you're ranging over both the indices and the values. In this particular case of dictionaries, you have to remember a different way of doing it. Okay, so you add a dot items, but it's never going to be any different from that. You just unfortunately have to remember enumerate is for lists and dot items is for dictionaries. Of course, you might not like this order. So you might say, well, the order that I put them into the dictionary is not necessarily special, but I want to present them to the user in some special order. And one of the ways may be based off of the decreasing number of values, I guess. So you would want to go through and update this in some way when you're printing, access them in a particular order. Or maybe you just want to print them out in alphabetical order. And for example, O comes before P, I think, in the dictionary. And so we might want to print Ohio and then Pennsylvania and then Texas. It's a natural sort of application. And I think it shows a way that in which we can work or manipulate with dictionaries. So let's do a quick application of that. So the first thing is that if you access electoral votes.keys, this gives you something that behaves somewhat like a list. So I don't want to delve into the specific details here. But I could set, for example, keys equal to electoral votes.keys. And I could print these so you can see them and see how it gets printed. Okay. And so you see that in large part, it kind of looks like a list of strings. Okay. So that means we can work with it in the same way that we would work with a list. And so I could sort the keys, and I can do that with a built-in function called keys.sort, and then I could print keys again. And here they're going to come in. I need to make sure that I convert it to a list, so this will work sometimes. Let me try it that way, and now everything's going to be okay. So I set keys equal to the list of this .keys function. And now I'm going to sort that list because this demands that it has to be specifically a list. And then I'm going to print the list. And you're going to see now all of a sudden the keys have been sorted Ohio, Pennsylvania, and Texas. So this changes the underlying list because, for the reason that you might imagine, keys is now a list. Lists are passed by reference. When you call this function, it's going to change it. And now if you want to range over the states, then what we're going to say is for key in keys. So now I'm ranging over the sorted collection of keys, and I'm ranging over a list, right? So I'm ranging over a list, but that list is the collection of state names. Okay. So I could even call this state name if I wanted to, because I know that the keys store the state names, and we're used to this way of ranging over a list, where if I do this, it's going to give me the values of the list. Great. If I've got the state name, that's what I care about. And then I could just say print at every point in time what we want, which is to print each state. So I'd say number of electoral votes in state name is, and then we need to access what those votes are, but I can do that with electoral votes of state name. And when I save that and run, what you'll see is when we print these, they're now going to come out alphabetically according to the order that we care about. So we have Ohio, Pennsylvania, and then Texas. Now, Python does have a faster way of doing this. I'm just showing you a way that is based off of some things that we might already know, which is that, well, I'm telling you that there's a built-in function for sort, but there's nothing wrong with knowing that you can go in and easily convert all the keys of a dictionary to a list. That's pretty useful, and that might be pretty transferable. All that having been said, all of this code can be done quite a bit faster. So there's a faster way of doing it, and this is a pretty common type of application. So I could point out that there's a faster approach. And I'll say that approach, I'll probably just comment this out, but just to say for state name in electoral votes, that's what I wanted to do. And I wanted to print this statement here. Number of electoral votes in the state name is electoral votes of state name. So this is giving me, again, we've seen this. This is ranging over the keys. This is what we initially did. So we ranged over all of the keys in the dictionary, and then we printed the key name and the value associated with it. In this particular case, all I have to do is just put sorted of electoral votes. So Python knows this is something that people might want to do frequently, which is to range over a dictionary based off of the ordering of whatever it is that are the keys, which in the case of strings, the obvious ordering is just going to be alphabetical order. So I did want to at least show you that to keep the Pythonistas happy, and it's a nice feature. But I'm going to keep it commented out since we only need to do that so many times. One more thing I should point out, we also can get just the values of a dictionary. So if we're interested, for example, if we look at our frequency table, the keys are going to be strings, the values are these things. These integers 3, 2, 2, 3, 1, 1, 1, and so forth. So if you're interested in those values, then what you might do is to say, well, I can get this with whatever the dictionary name is, and then values in parentheses. So I might want to imagine an application like, I don't know, we're going to count the number of electoral votes in total. And so I'll set the total number of votes equal to 0. Eventually I'm going to print that. Okay. And in the meantime, I need to do some kind of range. So in this particular case, technically, probably most of the time, you might just range over the keys and the values together using that .items approach, and then just ignore the fact that, so we could just do this, right? And I'll probably write it that way initially. So how we would say it would be range over the state name and the number of votes in electoral votes dot items. And then at each point in time, we could say total votes at each point in time, we're plus equaling whatever the number of votes currently is. And that will work. And I'll show you, we can save that and I'll run it. Total votes is 76. I presume that's what 40 plus 19 plus 17 is. I'm not very good at arithmetic because I have a PhD in math, as we've seen. But if this is right, then we know that the answer is 76. Great. And if we just cared about the values, there's an opportunity to just range over the values. So I want the values, which are not just the keys and the values together. And in this particular case, I want the number of votes. And when I do that, it's going to work. And you might say, well, it's probably not quite a list. So you do want to be careful there. If you want to use it in the context where a list is going to be used, then you need to do this and make it a list by force. Whether or not you do it, you're still going to get the correct answer. And so this is very useful in practice. That's it for the basics of dictionaries. And we've seen some applications that are eventually going to be, I'd say soon, they're going to be relevant when we look at trying to simulate a presidential election from polling data. But what we want to do is work more with strings for now. And so I want to come back to my idea of creating this dictionary of substrings and mapping each substring of a string to how many times we see it, and do this for all substrings of a given length in a string. So that's our motivating biological application. And that's what we should come back to. And I call that frequent words. So to get started with finding frequent words, let's create a new folder. New folder not in Dictionaries, but in SRC. I'll close this out. And that new folder is going to be called frequent words. And of course, I'm going to have a main.py in there. And let's copy over from some starter code for us so I don't have to type out my fancy 2 lines there. I don't know why it doesn't want to allow me to see main.py here. That is weird. What have I missed? Huh. Oh, I was making a folder. Interesting. Okay, well, let's get rid of my folder. Delete. Yes, I want to remove the folder main.py. Okay, let's try that again. So I'm in frequent words. This is a file. There we go. All right. And we're going to have my 2 lines there at the bottom that's going to say run what's in main. I'm going to go in and get def main and say, actually, by the time I do that, I could just write def main. And a lot of times, if you're seeing people who are writing this very precisely, we can use this idea of having a type hint and say main is not going to return anything. So I'm not usually going to do that, but I am going to point out that's not incorrect practice to do that because main is not going to return anything. But in the meantime, I'm going to say, what is this going to do? We're going to find frequent words in strings. So I'm going to range over a string and find all of its frequent words. And the function that I want, okay, which I'm going to write, is to say, let's look back at my table. I've got my frequency table here. This is our dictionary that I care about. And I want to make this thing for sure. But I'm going to assume that I've made this. And what I actually want is a list of strings that occur the most frequently. So what I want to produce is a list that says ACG and TTT are the most frequent substrings of length 3 in the underlying string. How do I know that? Well, because they both have the maximum value equal to 3. So with that given, the function that I want is going to be called frequent words. It's going to take a string that I'm going to call text, and it's going to take an integer that I'm going to call k, and it's going to return a list of strings. I should make sure that I have my doc string. So the doc string is going to produce all frequent k-mers. So a k-mer is a substring of length k. I should say most frequent k-mers in a longer string. So our parameters, our input, are going to be a text, which is a string, and this is going to return a list of strings. So this is a list of strings representing the most frequent k-mers in text. And we should probably check for errors. So this is the natural sort of function where we might encounter an error here. And the error that I first and foremost want to ensure that does not happen is what happens if somebody tries to give us a negative value of k. There's no such thing as a 0, or I really don't want to allow 0 either, because that's just the empty string. So I don't want the user to be able to input a negative value or a 0 value for k into this function. If that's the case, then I want to raise a value error. And I want to say something like error non-positive value of k given to function as input. The other thing I probably want to check is, well, what would happen if somebody tried to find a value of k, my substring length, that's longer than the string? That would be bad too. So if I did that, then I would need to just, maybe I raise an error, maybe I just return an empty list. That's a design decision I would imagine that I have to make. And then what is it that we want? We want a list, okay, in advance. Do we know how long that list is going to be? No, because it could have one thing in it. It could have two things in it, like the example that I showed before. It could have a million different substrings in it that all achieve this maximum. So just as we've seen before, if I have a list but I don't know exactly how long it needs to be, it makes sense to start it off as an empty list. And eventually, this is what I'm going to return. So I think about everything in terms of inputs and outputs. I'm going to create my list. At the end, I'm going to return that list. And then if you do our reading accompanying this material, then you will have seen what's the high-level idea that we present for doing this. I will refresh your memory of that, which is to say, well, the first thing we need to do is make our frequency table. So make this out of the underlying string, where every substring is mapped to its number of occurrences in that string. And I could think about how to do that, but I'm going to just say, let's assume that we know how to do that. So I will go ahead and I will put a comment here that says to generate the frequency table of text and K. So I'll say I'm going to do that. And then what's the next thing that once I've got that thing, what is it that I want to do? Well, I say, what's the maximum value? For the example I showed just now, it's equal to 3, but in general, we just want the maximum. And then once I have that maximum value, then I want to say, let's range over that frequency table and identify the strings, which are keys, that achieve the maximum value that we found. When we find one, append it to our frequent patterns. And now we've got an idea for how this function is going to work. And here's where we remember that we are not mathematicians, we're aspiring computational scientists. And that comes with, as we've seen, higher pay. I don't know about right now, but higher pay and not having to work as hard. And that's a good thing. So we aspire to being lazy. And in this particular case, I'm going to say, I will hand off the generation of this frequency table. We should be getting in the habit of any time I can just write a subroutine and say frequency map is equal to frequency table of text and K, and just hand this off and assume this is generated by this subroutine, which we will write, but now I'm going to say, now I've got the frequency table. So I'm assuming that I've already generated what we care about, which is this thing. And once I've got that thing, great, because I can work with it and just find the maximum value. So I could think about writing that code now too. Say, yeah, I've got to write the code to range through this thing and identify the maximum. But yeah, that sounds too complicated. I'm just going to say max value, or M, is equal to the max map value of whatever frequency map that I just generated was. And then we range over the frequency table and identify the strings that achieve this maximum value, which is M. So then we're going to say, how do I range over this? Well, it's a dictionary. It's got strings that are keys. It's got integers that are values. I care about both of them because I want to find anything that achieves a value equal to M. And then that's a string that I care about. So I'm going to say for pattern comma val in frequency map dot items. We get to use what we just learned. And if at any point in time the current value is equal to the maximum value, then I'm going to say frequency patterns dot append whatever the current pattern is. So I found a match. And I'm going to call this max val just so it's a little clearer and kind of consistent with that. And that's our function. All right. BZ says this was a technical interview question that they got one time and they did not pass. And my guess is, I'm sorry to hear that. I'm sure you're doing great now. But my guess is maybe you weren't lazy enough, right? So how can we aggressively think about, I want this function to be as short as humanly possible, right? And not necessarily because I know a bunch of Python tricks. I'm not meaning that, but I just mean I want to, my mind can only work in so many different directions at once. And this is a paradigm that we're going to see throughout this course, which is as the code gets more complex, a lot of times we got to make it much more simple. And so we have to have this, because a human is working with this, we need to bring everything back. And the natural way of doing that is through what we call modularity, or simplifying these complex tasks by using a lot of subroutines. So we have two subroutines. And here's going to be, I'm going to give you an opportunity to write one of them, because we're at the point where you know plenty. So for example, let's look at max map value. And yeah, we've done, sure, there's going to be built-in functions to make this easier. And we've done maximum of things before, but it's just good practice to manipulate dictionaries to say, I have a function. It's going to be called max map value. It's going to take, I'm going to call it map. And this is a dictionary of strings to integers as input. And then it's going to return a dictionary of strings. No, it's not. It's going to return an integer. Okay. And I'll just specify the doc string. For now, I'll say finds the maximum value in an input dictionary mapping strings to integers. And you know, I think that's enough. So sometimes you have a short function. I think that's plenty for a doc string. It's clear what the inputs and outputs should be there. I should have some error checking. If k is less than or equal to 0, I should probably raise a value error and say, even though I will have checked it in the higher level function, I should check it in the lower level function too. And I'm going to have the same error message. And so let's just say we'll have that same error message. And then the other thing I should check is if, what am I doing? I'm in the wrong place. I'm testing k. I was so comfortable writing this check. K is nowhere to be found. Hang on to this thought. We're going to have another subroutine where k is relevant. What should we check here? If length of map is equal to 0. Let's do that. Raise value error. And we're going to say empty map given. All right, that's better. So you don't want to give this thing something with no keys in it. That would just be rude. But in the meantime, you know how the function is going to work? Let's do this. It's your turn. You write this function, and you'll get a little bit of practice on working with dictionaries and ranging over them. And I'll give you a few minutes, and then we'll come back and discuss. Because we want how often the most frequent thing happens. So we want the maximum value in the dictionary. And that's useful when we have the subroutine, because I'm going to make the table. We're going to say what achieves the maximum, what is the maximum, and then what achieves that maximum. So we have like two separate steps of going through the frequency table and identifying first off what the maximum value is, and then, so in this particular case, we're just getting this thing, and then I want to return 3. And then we'll have a separate step that says, well, where does 3 occur? And they're two separate steps because you need to range through the whole thing to figure out where the max even is. It could be the last element. And then your other point would be, well, once I know what the max is, then what achieves that max? Another minute or so. Now, as pointed out by some folks in the chat, of course, there is a one-line version of this function, right? I could use the fact that there's a built-in max function in Python so already that will say, oh, if you give me a list, right, or something like a list, I can run through it and identify what the max value is. So I could just say max of map.values, right? And that's fine. That will work. The idea here is it's also not a hard function to write without using a built-in function. And it's good practice for the sorts of things that we're going to see. We're not far away from getting outside of the realm of what we can do with built-in functions. And at that point in time, we need to be comfortable thinking on our feet. And this function, writing it from scratch, is actually, it can be a little trickier than we might immediately think, in part because, well, when you have a list, it's a relatively straightforward function to think about how you find the max value in a list, because you say, well, if the length of this list is 0, okay, no good. Otherwise, I'm going to say, what's my first element? Like m is equal to, in the case of a list, it was a of 0. And then we would range over the other things, you know, and go from there and say anytime something beats the current value of m, update it. But there is no like map of 0. There's no initial element because there's nothing special about the order of these things. And so instead the question becomes, how do you find that? There's a number of workarounds. We could have a loop that goes through and says we could have a Boolean flag, for example, and set it equal to true. And then every time through the loop, it sets it to false. So it's like a light that starts off as on, like I've not gone into the loop yet. And then the first time through the loop, the light is on. So we say, oh, set m to be the current element, and then flip the switch off. And every time next through the loop, the switch is going to be off. And that's a nice little clever trick in terms of how to do it. We don't have to do it that way. I mean, I think a better way is to use the fact here that I told you that we do have a dot values list, or something that's like a list. And so I could say that vals is equal to the map.values that we care about. Let's go ahead and convert it to a list, just so I'm positive that we're working with a list here. And then I can say the first element in that is going to be equal to our first value, initial value for m. And then I'm going to say for val in this collection of values that we have, if you ever encounter a value that's greater than m, well, then I'm going to update val, or m, to be equal to that current value. And then at the end of this, I'm going to return m. Okay. So yes, there's a one-line version of the function, but it's good practice to write the 6-line version of the function because it's not really any more complex. That was our practice function. The other function I care about is I want to write a function, you'll see it's underlined here in yellow, that I've not implemented. It's the other subroutine that's part of the frequent words function. And so to write this function, what we need to say is, well, first off, it's going to be called frequency table, and it needs to take a string text as input as well as my integer k. So I'm giving both of these inputs that the frequent words function is taking, and I'm passing them into this. And I need to remember that it's str in Python. And then it's going to produce, well, the frequent words function produces this list of frequent k-mers. But what the frequency table needs to produce is our frequency table. There it is. Our frequency table is, of course, this dictionary that maps strings to integers. And so I need to specify that in the type hint and say it's a dictionary of strings to integers. And then I'd hit colon. And I'm going to have the same checks that I had before. So let's do the same exact thing. I'm going to say if it's the case that k is less than or equal to 0, that would be bad. I don't want k to be less than or equal to 0. And if k is greater than the length of text, well, I'm going to return an empty dictionary. And you might say, why do I have to do those checks? Well, somebody could come along and call this function and want to generate the frequency table for another application. And if they did that, then you want to make sure that you have your parameter checks here as well. I also should have a doc string. So I'm going to say generates a frequency table mapping k-mer substrings of a text to their number of occurrences. Okay, and we'll say that the parameters here are text as a string, and we also have k as an int. And then what is this going to return? This is going to be a dictionary of strings to integers. Keys are substrings of text having length k. Values are the number of occurrences of that substring. And there we go. We, of course, have to write the function. But now we know what we're doing. How's this function going to work? We need a dictionary. And we know that that dictionary needs to have this specific type. So let's call this thing freak map. And I'm going to say it is a dictionary of strings to floats. I don't know how big it needs to be in advance, because I could have a very long string that only actually has one substring. So if the string was like like a bunch of A's, right? Well, that only has one substring of any length, and it's just a bunch of A's. So I don't know how big this dictionary will be in advance. I need to range through and make each particular element as I encounter it. So we'll start off with an empty dictionary. Way down here, I'm doing this for effect. Eventually, we're going to return this frequency map. Okay? And again, this is the way in which I want you to think about writing functions, which is the first thing that you do, probably is specify the doc string and do some parameter checking. But when you're writing the function, the first thing you should do is to establish what is it that this thing's going to return, and do I need to create an initial version of it, and then make sure that I type return that thing at the very end of the function. Just good practice. Then it's just a matter of saying, okay, in order to make my table, what I want to do is I want to slide a window along the text. And we've had a little bit of practice with this already when we talked about counting the number of occurrences of a pattern in a longer text. So we've seen a simpler version of this, but it was warming you up to this idea. And we also, remember, we extended that to not just count the number of occurrences, but to list where they come from too. So we're going to get to practice this idea of sliding a window along the text of length k. And in other words, this is range over all those substrings of length k. And we know how to do that. So there are some number of substrings of text of length k. Here's our review exercise. I want you to think about, if I set n equal to the length of text, a very courteous thing to do. Remember, how many substrings of text are there? I'll say Kmer substrings. What's the answer here? This is a review. It's not K. It's not K. We can see a counterexample to that if we look at our form of frequency table, right? Where we see K is equal to 3. There's definitely a lot more than 3 substrings there. So it says NK1 something, some arrangement of NK and 1. Good. And a few people have it now. Yes. So the answer is n minus k plus 1. So if we want to range over all of the Kmer substrings of a given text, we know that the starting positions of those substrings start at 0, because since everything in Python is 0 indexed. And then so we go from starting positions 0 up to starting position n minus k. Okay. So that will give us n minus k plus 1 total things, because we're starting our counting at 0. Now I can do that then with saying for I in range of 0 up to n minus k plus 1. So we have that convenient way of grabbing n minus k plus 1 total things. These are going to give us the indices corresponding to the starting positions of these substrings. Anytime we start off with a 0, we don't need to specify that. What's our current pattern? Our current pattern is the substring of text, and this is a review too, starting at position I, going up to but not including position k. And you will remember, I hope, that this looks initially confusing if you haven't seen substring indexing like this in the past, and I understand that. But the natural way of thinking about this is the top index minus the bottom index gives you the length of the substring. And so I plus k minus I is k. And now you say, oh, how I'm really viewing this is this is the substring starting at position I of length k, because I subtract those, I get k. Now, everything here is a review so far. Okay. What isn't a review is we need to ask a question, which is, have I seen pattern before? Because this is an important distinction. In this particular case, like, in other words, does it exist in the map? And that is an important question. Why? Because I take 2 different actions. As I'm ranging through the string, if I've not seen the pattern before, then what I want to do is create an entry in the dictionary freak map associated with that pattern. If I have seen it before, well, I've seen it 10 times and I'm ranging the window. Well, this is time number 11. I just need to add one to it. So here's where we get to practice knowing how to check if something is in a dictionary. I can say, oh, I remember that. I can check if something is a key of a dictionary. I can say, is it the case that pattern is in frequency map? Okay. So if so, this says I have seen it before. And in that particular case, all I have to do is say freak map of pattern plus equal to 1. Then I say, if that's not the case, well, we probably should add a key value pair for pattern. So this is no, I have not seen it before. If I haven't seen it before, well, I set frequent map of pattern equal to the number of times I have seen it. And I've had seen it 0 times up until now, but now I've seen it 1 time. So I'm going to set frequent map of pattern equal to 1. At the end of this, I'll return freak map. This perfectly fine function. This will work. One critical point is that there is a simpler way of going about this. I like this a lot. Absolutely no problem with it. But there is a shortcut. And the shortcut is, in Python, if you call the function dot get, it has 2 parameters. parameters. It has two parameters. It has a key, and it has a default value to assign the key if it's not in the dictionary. Okay. I'm putting that on its own line. It returns something very specific. It returns the existing value if the key is in the dictionary, and otherwise, meaning if it's not in the dictionary, it does something neat, which is it sets, or I'd say creates this key in the dictionary and gives it the value of that was given as a parameter. So we'll see an example of this. Remember I said there's a default value to give it. So if it doesn't exist in the dictionary, we're going to give it that default value. All this will be much clearer if I just show you how it works. So in this particular case, I can do this in one line. Like all this code is just going to be one line of code, which is going to be a good shortcut. And I'm going to say freq map of pattern is equal to what happens when I go in and say, can we get it? Okay. So go in and try and get it. If you don't get it, give it a value of 0. If you do get it, add 1 to it. And so in both of those cases, I want to add 1 to the result. Okay. So, and I could do this in 2 lines. I like just doing it in 1 line because sometimes the Python one-liners are really annoying and hard to read. This is a nice, pretty one. So I go in and I say, is pattern a key of freq map? If so, cool, it's already in there, and add 1 to it and update it. If not, create it. Freq map of pattern gets created by this, and go in and create it, and then add 1 to it, which is what we want it to be too. So you have this nice short 1-line piece of code here to achieve the same thing. Okay. So I hate deleting this because this is so nice, but I don't want to do the same thing twice. So let's do that. I guess I could comment it all out. All right. Now, we have a working freq map function, I hope. And so we can make a frequency table of any text for any string text and any input integer k. We can make the frequency table, and we can then presumably find the frequent words. So here's an opportunity to run our algorithm and wrap up what we're doing. And I'll go into main. And in main, I'm just going to say, I think I'm up here in main somewhere. No, main was the other direction. Oop. Where is main? Did I not have a main? Oh, there it is. It is at the top. Okay. So I'm not actually run anything here, which what I should first do is navigate up a directory since I was in dictionaries, and then navigate down to go into frequent words. So I'm in the right place. Make sure my code is saved. And then let's give it an example. So to run this, let's do text equal, and I'm going to give you the text that I was interested in that generated the table that I showed you. So it's a very specific string. It's ACG, and then 4 copies of T, and then Lady Gaga, and then CG, and then ACGC. All right, and let's set k equal to 3 so that we can match the frequency table that I showed you. And let's print freq map of text and k. And I could print it in a nice way and go through the ranging. Not freq map. I'm going to print frequency table, I think I called it. Yeah, there we go. I called it frequency table to be a little more precise. And I could go through and do a range over that thing and print it in a nice way. We've already practiced that plenty. So in the command line, I'm going to just run Python 3 or Python if I'm on a Windows machine, main.py, and hit enter. And now we see our map that associates substrings with their number of occurrences. And I hope this looks vaguely similar to what we have here. All right. Do I have a slightly different string? I might. If I do, it appears to be working anyway. Okay. But we have ACG here and TTT there. Right. And so we can see that they're the most frequent. And what we really want to do is be able to identify those. So I really want to say that the frequent words and what they are, try to put a colon there we go, is frequent words of text and K. And so when we print that, and again, I could print that in a nice way, but it's not a very long list. We see that the most frequent K-mers of length 3 in this string are ACG and TTT, which makes sense. We see it in the table. ACG occurs 3 times, and TTT occurs 3 times as well. And so what we should do is we should, test this on a lot of different inputs. We should try a string that's just a bunch of A's. We should make sure that this works when K is equal to 1. We should make sure that this works when K is equal to the length of the text. What happens if everybody occurs just one time? These are the sorts of things we can check our code against the autograders that we already have prepared for you. But assuming this seems to be working, I want to do one more thing. And the one other thing I want to do is connect this back to like a biological example. So we could look at a specific region that we're interested in solving this problem for. And that particular region is the replication origin region of about 500 nucleotides in the bacterium, which is V. cholerae, that causes cholera. And so I'll say V. cholerae ORI, to be precise, is equal to this string. And I may as well just put it in the chat. It's not going to let me put it in the chat. It's too long. That makes sense. But it's not hard to get this string off of our website. So go there and you can copy it in if you like. And that's the experimentally verified replication origin of this bacterium. Then what we want to do is to say, all right, cool. What are the frequent words, or what's the frequency table of this? So I could say print the frequency table of, and I probably should update K. Well, let's set K equal 3 again. Print the frequency table of, I called this V. cholerae ORI, and K. When I save that and run, it's going to be a big table. Okay. And this tells us that how many times each thing occurs. I will also print the frequent words themselves. And what we're going to see is, for this string, and this value of K, when I hit the up arrow and run it again, I get TGA is the most frequent substring of length 3. And we can see it, actually, it's up here lurking in the table. TGA occurs 25 times. Now, proteins bind to DNA regions that are longer than 3 nucleotides long. So I don't necessarily want to run this just for K equal to 3. I want to run it for longer values of K, but I will show you at least that this is working for other values of K. And we could range through here and find ATGA. I think it occurs like 12 times or something like that. But we want to look at something like K equal to 8. And that gives us one substring. Interestingly enough, when I set K equal to 9, and I run this, then we get 4, substrings of length 9 that occur the most frequently. So they achieve the maximum. And one of the things that I might do is to say frequency table is equal to this thing. So let me do this, and then I'm going to print frequency table. And then I say, how many times does each of these words occur? Well, I could say print freq table of one of these strings, since they all occur the same number of times. So I'm going to put it in quotes. And I'll just say the maximum is this. So the maximum number of occurrences is 3. And what we find is that there's 4 different substrings that all occur in this particular region 3 times. So this is indicating that maybe there is, some signal here in terms of it's occurring as 3 separate occurrences of these pretty long substrings in what ultimately is not that long of a region. And I would appeal to our website which explains that there's more even to it than meets the eye. So one of the things that you might notice is that this string here is very similar to this string here. In fact, it's just us having a C latched onto the start of the, or a T, excuse me, latched onto the start of this string. So it's TCTT, GATCA instead of CTT. And then there's CT, CTT. So if you add a C onto the start of that string, then it occurs 9 times as well. So it's a little bit, what you found is that actually there's a string of length 11 that occurs 3 times. And that's kind of interesting. But the more interesting thing is that if you look at this string and you say, well, this string, ATGATCAAG, appears to be not related to these other 3. And yet when you consider its reverse complement, then you go CTT, GA, TCAT. And when you spell that out, that's the exact same thing as CTT, GAT, CAT. So you don't actually see 3 occurrences of your pattern. What you're really seeing is 6 occurrences of a pattern, where 3 is this string and 3 is the reverse complement. So this is something that's very statistically significant, because the protein that's coming in and binding is not intelligent enough to know which strand of DNA it's latching onto. It may latch onto one strand, or it may be latching onto the complementary strand. And this is giving it 6 different opportunities to bind. So that's pretty neat. And it shows that one of the things that we should do maybe is maybe we could add reverse complements into the frequency table. And that would make it that much more complex, because your keys then would be a string as well as its reverse complement. And you'd have to combine those 2 in some way to say anytime you see either of these strings, then you want to update the value associated with that particular key in the table. Now, for now though, I think that's a great stopping point. What we can do for now is we can find words in a short region that are of interest. So something that's occurring frequently in a short region. And if we know where to look, that's a biologically useful starting point. So if you know that here's a region of interest, and you know that a protein has to be binding here, we can add to this by adding reverse complements to it. We could maybe even add potential mutations to it, so we're finding frequent words with mismatches. This is the sort of thing that we do in our bioinformatics algorithms textbook project, which is more advanced applications of this specific question, which you're welcome to check out. And we even have like public-facing Roslyn questions around them. But my question for now is I want to go in a slightly different direction, which is I can give you the short region and we can find frequent words in it. But what if we have the entire genome? How did we know where to look in the first place? If you look at the Vibrio cholerae genome, the whole collection of its DNA, it's several million letters long. And so what we really need is an approach that's going to find all the places in that genome where you see frequent words. So all of the short regions within the long genome where you see surprisingly frequent substrings. That's going to be work for what we do next time. And so I hope you'll join me then. As always, please like and subscribe if you enjoyed what you saw today. Like, subscribe, and connect with us in all the ways that we provide those connections. But that's enough for now. Until next time, happy coding.